Now we come to module 2 of chapter 1. In this module, I shall describe the genesis of Volterra integral equation. Here, I shall consider Abel's problem, rather Abel's integral equation, how it comes from Abel's problem. Abel's problem is often referred to as Volterra integral equation of first kind. Next, I shall show how the initial value problem can be reduced to Volterra integral equation of second kind. Now we shall derive Abel integral equation from a well-known problem of mechanics, which is as follows. A smooth curve x equal to psi y, where y lies in the interval 0 to b with psi 0 equal to 0, is held fixed in a vertical xy plane. Now the problem is to determine the time a particle of mass m takes to slide freely under gravity down the curve from any point capital X, capital Y on the curve to the lowermost point, the origin. This may be thought of as a person sliding down a roller coaster, say from a specific point to the ground, and the problem is to determine the time taken by the person to slide down the roller coaster starting from a point, particular point, to the ground. Assuming that the particle started to slide from rest from the point capital X, capital Y, we have from conservation of energy that half mv square plus mgy equal to mg capital Y. That is, the total kinetic energy and potential energy is constant. Here, v is the speed of the particle at time t when its position is given by small x, small y, and g denotes the acceleration due to gravity. If s represents the arc length of the curve measured from origin to the point small x, small y, we can write the speed v as ds dt, so that we can express the equation 1.2 by writing v equal to ds dt in the form given by ds dt equal to minus of root over 2g into capital Y minus small y. Here the minus sign is used because the particle is descending, therefore s is decreasing with time t. Now we know the well-known formula of calculating the arc length, ds dy equal to 1 plus psi dash y whole square to the power half. Here psi dash y denotes the derivative of psi with respect to y. Now using ds dy as given by equation 1.4 and ds dt as given by equation 1.3, we can write dy dt in the form given by equation 1.5. Now integrating dy dt, we get the relation as given in equation 1.6. Here integral y starts from capital Y to 0, and if capital T is the total time of fall of the particle from capital XY to the point 0, 0, that is origin, then the total time of fall capital T is expressed in equation 1.6. Now if I write phi y equal to 1 plus psi y square by 2g whole to the power half, then equation 1.6 can be written in the form given by equation 1.9. Here the total time of fall capital T in equation 1.6 is a function of capital Y, the initial point capital XY from where the particle started to descend. In equation 1.9, we may note that f of 0 is equal to 0. So, we find that the problem of determining the time of descent capital T, that is f of capital Y of the particle, can be known by using the formula 1.9 if phi y is known. Now phi y, as we remember, that it is related to the shape of the curve x equal to psi y through relation 1.7. So if the shape of the curve is known, then from equation 1.9 we can determine the time of descent. Now Abel modified this problem and thought of the converse of the problem, that if the time of fall is specified, then can we know the shape of the curve? This problem is historic Abel's problem. That means from 1.9 equation we see that if Fy, that is the time of fall, is specified, then we have to find the shape of the curve for which, if a particle starts descending from a fixed point capital X capital Y of the curve, he will reach the ground or 0, 0 point in time t. So that means same problem, how the roller coaster should look like if the particle is set to descend through that roller coaster in a given time. So in equation 1.9 we see that the unknown function phi y appears under the sign of integration, and so it is a integral equation of first kind of Volterra type. And this is the Abel's integral equation. Next, we shall consider initial value problem for ordinary differential equation and show how the initial value problems can be reduced to Volterra integral equation of second kind. We shall consider few examples to show how we get Volterra integral equation of second kind. We consider example 1. Let the function phi x satisfies the following initial value problem: d phi dx equal to capital F of x phi x, x lying between 0 and 1, and the initial condition phi at x equal to 0 is phi naught. This is a first order differential equation, and we assume that the function capital phi is integrable for all continuous functions small phi x in the closed interval 0, 1. We simply integrate this differential equation to obtain phi x equal to 0 to x capital F t phi t dt plus phi naught, where x lies in the interval 0 and 1. This is a Volterra integral equation of second kind. As is seen from this relation, the upper limit of integral equation is x. Now we come to the second example. We consider the function phi x which satisfies the following second order ordinary differential equation given by d2 phi dx2 equal to capital F, which is a function of x phi x. X lies in the interval 0 to 1. And two initial conditions are there. Phi at x equal to 0 is phi naught, and phi dash at x equal to 0 is phi naught dash. Here I must mention that dash represents derivative with respect to x. Here also we assume that capital F is integrable and phi dash are continuous in the closed interval 0, 1. Now I write the given differential equation in the form phi double dash t equal to capital F t phi t, and integrate this differential equation with respect to t from 0 to x, and we use the initial condition phi dash 0 equal to phi naught dash to obtain phi dash x, which is equal to phi naught dash plus 0 to x capital F, which is a function of t phi t dt. Again we integrate this equation and use the initial condition phi at x equal to 0 equal to phi naught to obtain phi x equal to integral 0 to x integral 0 to s f of t phi t dt ds plus phi naught x plus phi naught x lies in the interval 0 to 1. Now the double integral 0 to x and 0 to s ft phi t dt ds can be further simplified by interchanging the order of integration in a standard manner. Now the inner integral is t integral, which varies from 0 to s, and the outer integral is s integral, which varies from 0 to x. So in the Ts plane, the line s equal to t is drawn on which the point xx is given, and we denote the region of integration in this triangle. Now we interchange the order of integration. T integral should be the outer integral, which varies from 0 to x, and s integral will be the inner integral, which varies from t to x. Now, performing the s integration, we can rewrite the relation containing phi x as given in equation 1.12. This equation 1.12, here phi t, the unknown function, appears under the sign of integration. The range of integration, we see that from 0 to x. So the upper limit of integration is variable, and phi x also appears free from integral sign. So this is a non-homogeneous Volterra integral equation of second kind. So we see that initial value problems give rise to Volterra integral equation of second kind. Now we shall consider a problem. Problem 1, we consider the initial value problem given by phi double dash x equal to x phi x, where x lies between 0 and 1. The initial conditions are phi at x equal to 0 is 1, and phi dash at x equal to 0 is 0. Here dash and double dash represents differentiation and double differentiation with respect to x. Now this problem, if I compare with the previous problem in example 2, we see that capital F, which is a function of x phi x, is given by x phi x in this case, and phi naught equal to 1 and phi naught dash equal to 0. So following the same procedure, we can easily see that this initial value problem is equivalent to the following Volterra integral equation of second kind given by phi x equal to 1 plus integral 0 to x minus t phi t dt, x lying in the interval 0 to x. Next we come to problem 2. Here we have to convert the following differential equation along with initial conditions, that is the initial value problem, to an integral equation. The problem is given by x plus 1 whole square y double dash x plus 2x plus 1 y dash x equal to fx. Y at 0 equal to alpha and y dash at x equal to 0 is beta. Here fx is a known function and alpha and beta, they are known constants. We shall try to reduce this initial value problem to an integral equation. Now we write the given differential equation in the form t plus 1 whole square y double dash t plus 2t plus 1 y dash t equal to ft. And we integrate this equation with respect to t from 0 to x and use the initial condition y dash at x equal to 0 equal to beta to obtain the relation given by x plus 1 whole square y dash x equal to 0 to x integral ft dt plus beta. Again integrating this equation and using the first boundary initial condition y at x equal to 0 equal to alpha, we obtain yx in the form x plus 1 whole square yx equal to alpha plus beta x plus 2 times integral 0 to x t plus 1 yt dt plus double integral 0 to x and 0 to s ft dt ds. Now, as done previously, we interchange the order of integration in the last term to obtain the relation x plus 1 yx minus 2 0 to x integral t plus 1 yt dt equal to alpha plus beta x plus integral 0 to x x minus t ft dt. Here we see that the unknown function yt appears under the sign of integration as well as it appears free from sign of integration. Also, the range of integration in the second term on left hand side, we see that the upper limit of integration is a variable. So, this is a Volterra type non-homogeneous integral equation of second kind. In this module, we have seen how an initial value problem can be reduced to Volterra integral equation of second kind, and the Abel's problem gives Abel's integral equation, which is often referred to as Volterra integral equation of first kind. With these few words, we conclude Module 2 of Chapter 1.